this video I'm going to look at several little parts of the homework questions that you might want a bit more support. Great opportunity to revise and think about everything we know about filament lamps, because this question is all about a filament lamp. Okay, so a filament lamp is an old-fashioned light bulb, isn't it now? So it's where you've got your wire inside that bulb of inert gas, and as the current flows through the wire gets so hot that it emits visible light. So remembering that, as soon as we start to read this, thinking about the fact it's a filament lamp we're being asked about, and we know that a filament lamp, that piece of wire in there, does not obey Ohm's law because it's getting hot. And as things get hot, as wires get hot, there is an increase in resistance, because as the wire gets hotter, the ions of the lattice are vibrating more. There are even more collisions between the electrons and the ions of the lattice, and so the resistance goes up. So when we look at the current voltage relationship, we don't see this straight line, we see that S shape when we think about filament lamps, because what's happening is that you haven't got a fixed resistance. It's not obeying Ohm's law. So, thinking of that knowledge as we move into the question, the number of batteries here is increasing. And as the number of batteries increases, as you go down the table, the voltage is increasing. And as you go down the table, the current is increasing. So voltage, as you supply more energy per unit charge, you get a greater rate of flow of electrons. Okay. However, as I was saying a minute ago, this is not a straight line graph, not for a filament lamp. And that's because this relationship is not proportional. So voltage increases, the current increases, but not proportionally. One way of showing that very simply is as you double the batteries from 1 to 2, the current doesn't double to 120 from 60, it only gets up to 83 milliamps, and that's because of resistance. So we've got to mention that. So we've got our first mark, we've got the idea that voltage is increasing, current is increasing, but they're not doing that in proportion to each other, because there is resistance, and the resistance is increasing. Because the resistance is increasing, those collisions, there's more collisions between the electrons and the ions of the lattice. As they're colliding, more energy is being transferred and the wire is warming up, and that's why what you want to happen if you want to emit light, you want it to get so hot that it emits visible light. But the resistance is increasing because the temperature is increasing, and that's where the explain bit comes in. It's linking these together. So this is our analysis. As voltage increases, current increases, but not in proportion. This is our explaining bit, because the resistance of the filament lamp is not fixed. The resistance is increasing because the temperature of the filament is increasing. And that's how we should get ourselves the 3 marks. In this question, we've got to identify why this circuit isn't going to work. And the first thing I noticed, maybe you did too, is this alignment of the cells at the top there. So we're trying to make a battery of 2 cells, but you need to turn one of them round. So it wouldn't matter if you kept this one on the left the same and turned the other one round, or you could turn them both this way. It wouldn't matter which, but you need to turn one cell round and leave the other one alone. That's one thing to correct. Another thing are these meters. So ammeters measure the rate of flow of electrons. We need the electrons to flow through the meter. So we need to have ammeters in series. So this meter here should be an ammeter in series to measure the current. And then voltmeters. So this should be a voltmeter, they were around the wrong way. A voltmeter is measuring the potential difference, so the energy difference either side across the device. So you always put voltmeters in parallel. So ammeters in series, voltmeters in parallel, and the cells working together So we're being asked to compare and contrast how the resistances of component A and component B vary with temperature. We're analysing these graphs to look at comparing and contrasting similarities and differences. So first of all, a similarity, they are both resistance temperature graphs and they both have the resistance changing with temperature. So the same, I would talk about resistance changes with temp. Excuse my scribbles. Something else that's similar about them, neither one of them are a straight line. Both graphs are what we call non-linear, both curves. Both relationships are non-linear relationships. However, before we get to differences, I think I've spotted one more, because at 5,000 ohms, 80 degrees temperature, and at 5,000 that's still. If you look at the resistance of 5,000 ohms, on both graphs the temperature is 80 degrees Celsius at that particular resistance. So these two components, and they're not asking us what these components are, you may have worked that out, but they're looking for what's the same about these two graphs and what's different about these two graphs. So I think we've done pretty well finding three things the same there, and you're only going to need probably, like, for 3 marks, one similarity and one difference explained clearly and well. Looking at differences, the one that jumps out at me is this component A. As temperature increases, the resistance is decreasing, whereas for graph B, as the temperature increases, the resistance is also increasing. Non-linear, but that's a key difference. That's the first one that jumps out at me. Another difference would be where the resistance is changing the most, the temperature range. So where is the graph the steepest? And in graph A, the steepest part of the graph is right here at the start. That's where the gradient is steeper. But in graph B, it's here at the end. So for graph A, or component A, the biggest difference to resistance is at cold temperatures. So a small change in temperature makes a huge change in resistance if the temperature is cold and getting a bit colder. Where for B, that bigger difference in resistance comes from the hotter temperatures. So hot temperatures affect the rate of change of resistance more. So you could comment on that. Another thing that you could comment on as a difference between the two is the idea that both these graphs have a level, a plateau part, a constant part. But in graph A, the constant resistance is when the temperatures are hot, and for B, the constant resistance in B is when the temperature is low.